because two people have to take the test at a different time because of different scheduling things, I want to make sure I give as much preface just for the types of questions we're going to see on the test now. So there are actually 2 questions on significant figures, 1 question on the scientific method. There are a couple questions on vectors, one like identifying is this a vector or scalar. There are 2 problems with vector addition, one that you graphically add 2 vectors together, and one where you take the same 2 vectors and analytically add them together. And then probably the bulk of the problems are in 1-dimensional and 2-dimensional kinematics. So the problems, 1- and 2-dimensional kinematics. The questions are, the knowledge questions are more focused on the other things. So, and then there's questions about, like acceleration of gravity and things like that as well. But those are the things to look at. So the homework, that you've been working on for a week now, I signed it a week ago today, is dealing with this last thing for the most part, the 2-dimensional kinematics. And there were a couple of problems that dealt with one aspect that I haven't talked about, and that is relativity. Now, when I say relativity, of course, you should go, what? Relativity, Galilean relativity, is understanding how the motion of one object compares to a reference frame. So I've used this example like 3 times already, but I'll use it again because it's the one that makes the most sense to me. If you have a bus, and the bus is traveling at speed of the bus with respect to the earth is equal to, let's mix it up and say 15 meters per second. And you have a person on the bus. Let's start with something really easy. Let's say the person is just sitting here stationary on the bus. The speed of the person with respect to the bus is equal to 0. If the speed of the person with respect to the bus is 0, and the speed of the bus with respect to the ground is 15 meters per second, then how fast is the person moving with respect to the ground, with respect to the earth? It's 15, right? That was really simple and obvious. Now let's make it at least a little bit more interesting and say that the person is moving the same direction as the bus at 1 meter per second. Now how fast is the person going with respect to the earth? I'm not putting vector signs because it's 1-dimensional, but technically these are vectors, so technically I should have vector signs over these. I don't do it because I didn't put directions. The plus sign means the positive direction. My sign means the negative direction. Okay, so how fast is that person moving with respect to the earth? 16 meters per second. And I assume that everybody came up with that because it's pretty obvious. You're moving the same direction as the bus, and so you just add the velocities together. Now, at the end of second semester, when we talk about relativity, we will learn that this is only true if you're going at a slow speed. If you're approaching the speed of light, this isn't true. If if this was 0.15 times the speed of light and 0.1 times the speed of light, you wouldn't be going 0.25 times the speed of light, which is a little distressing, isn't it? Because it seems so obvious that you should be. Or, excuse me, yeah, I said 0.1 and 0.15, so I did that right. Now, mathematically, the way we calculate this is we took the velocity of the person with respect to the earth is velocity of the person with respect to something plus the velocity of that same something with respect to the earth. So notice the first subscript here is the first subscript in that first one. The second subscript was the second subscript in the second. And then the 2 inner ones have to be the same. And so in this case, the velocity of the person with respect to the earth, the bus is the only other thing we have, so it's going to be the bus here and here. And so that's the general rule for how you add velocities to get the change from reference frame. So you just look at those subscripts and make it so you add 2 such that the 2 subscripts in your initial one are the first and the first one, the last and the last one, and the inner ones are the same. Now, there's one more thing that can be a little bit of a difficulty. We had the velocity of the person with respect to the bus and the velocity of the bus with respect to the earth in, well, one of your homework problems. You have the quarterback is dropping back and he throws the ball while he's going backwards. Everyone knows you don't want to throw the ball when you're going backward. You want to plant and fire, right? But football and physics, they made it harder for us. He keeps running back and throws it while he's running back. He's going to have to put a little more, as they say, mustard on the ball, throw it a little harder to compensate for the fact that he's moving backward. And so the problem asks you what the velocity of the ball relative to the quarterback has to be. Well, the quarterback throws the ball, so the first thing you have to do is calculate how fast will the ball be traveling when it leaves the quarterback's hand with respect to the earth, because that's what we've learned to do. And after you calculate what the velocity of the ball will be with respect to the earth when the quarterback throws it, then you have to use this addition of velocities to calculate the speed of the ball with respect to the quarterback. But if we look at the problem, you're going to, step 1, calculate the velocity of the ball with respect to the earth. And then step 2, add to change reference frame. So you want to find the velocity of the ball with respect to the quarterback. Using the rules I just laid out, what are the subscripts going to be for those 2 velocities? What should the first one be? Velocity of what? Look at the red equation to get your subscript. Okay, it's going to have to be ball. What's the second subscript going to be for the second one? Q. And then we have to say, okay, well, what are the subscripts going to be in between? Well, clearly for the ball, we have ball earth. So it's going to be earth here, which means this one has to be earth as well. But we were given the velocity of the quarterback with respect to the earth, not the velocity of the earth with respect to the quarterback. So how can I calculate the velocity of the quarterback with respect to the earth if I know the velocity of the earth with respect to the quarterback? All right, I said that backward. How can I calculate the velocity of the earth with respect to the quarterback if I know the velocity of the quarterback with respect to the earth? What was that? It's just negative. It's going to be the same magnitude. The speed, if you say the quarterback is stationary, the earth is moving underneath him, the speed the earth is moving will be exactly the same as the speed that we would normally say the quarterback's moving, the earth is stationary, exactly the same. Kind of like if, Lauren, stand up. So, if Lauren walks toward me, we might say Lauren's walking toward me in 1 meter per second. But if you had a camera that was fixed on Lauren and you couldn't tell, you would say, instead of Lauren walking toward me, it would be Richard approaching Lauren. But the time that it takes for us to meet is going to be the same, whether it's my perspective or her perspective. So that means the distance divided by time is going to have to be the same. I just want the distance divided by time is going to be the same, so the speed's the same. The difference is, me standing here, I see Lauren coming this way. But Lauren there would see me coming that way, so we have opposite directions. So the key there is that if you flip the indices, you just change the sign. So we're given this, we then can put in just minus the velocity of the quarterback with respect to Earth, and we have everything we need. So now there is a third step on that. I didn't even talk about third step because third step is pretty obvious. Once you have found the speed of the velocity of the ball with respect to the quarterback, then you can find Pythagorean theorem to find the magnitude and tangent to find the angle. So the one thing that I didn't talk about there that you needed was how to change the reference frame. And you actually need that in both that one and, well, I think it's problems 4 and 5. You have to change the reference frame. So I need to cover that since the homework is due tonight. Any questions about, we will talk about the test on Monday. That's what Monday's lecture is going to be. There's no reading quiz for Monday because Monday's going to be a review lecture. And homework from today's lecture won't be due until Wednesday after the test. So your time after you finish this homework is free for studying for the exam until, after it's done. Go ahead, Noah.
But the stuff that's on the homework that's due Wednesday is going to be on the test?
It is not. The test is only through chapter 3. 3. Erika.
So talking about the quarterback moving backward.
Yeah.
Since it was turning to a negative, the quarterback thing. So then would the quarterback walking backwards be positive in a way? Because
Well, yeah. So you had she's talking about the specific problem. The problem says the well, let's just go to the homework help where it's all worked out for you, sadly. Yeah. It says the quarterback is moving straight backward. So his speed is in the backward direction. Notice I identified my directions. And so since it was backward, it really was a minus 1.3 meters per second because of the direction. And so then when you take minus this velocity, then it's going to be a positive in the x direction. That's what you're asking?
Yeah.
Yeah. Okay. Because I think this is kind of important, especially as we're preparing for the first test. By a show of hands, how many people do not have access to OneNote? Okay, so just the one. Okay, we will have to rectify that. Okay, little reminders. Come on. Tonight is, I don't know what they actually call it. I call it Harvey's Shindig, but I'm sure that's not. It's like Harvey's Harvest Festival or something like that. But basically, it's Vespers out at Harvey Meyer's place. And if you don't have a ride, I think it's leaving, is it Prescott Hall at 5:30? They'll provide rides. If you're driving, well, the address is given, and there's very limited parking, it says, so make sure you carpool. And then Saturday night, we yes, because I will be up there with the choir singing one little song, having a benefit concert for Harvey the Hurricane, not for Harvey Meyer. So that's at 7 p.m. at the church if you want to come and hear music. Now we're going to start talking more about forces. Forces, I said last class period, anything that pushes or pulls. Isaac Newton is really important in the discussion of forces. He came up with some laws that help us relate forces. And I always have to talk a little bit about Isaac Newton, in large part because my brother is a lot like Isaac Newton. Isaac Newton, when he went to school, he did not really care what the teachers were teaching about. He was bored. Now, was he dumb? No. No, he was very smart. I think we all agree he was very smart, but he was bored, right? The teachers were talking about stuff he already knew. What's the point? And so he spent it, from what I've read, he spent his time in class doing things like making little inventions to impress the ladies. And so by the time he finished the mandatory schooling, which, once again, I've read a few history things on this. I'm not a big history buff. It was like 6th grade. They said, okay, this guy's a failure at school. He does not pay attention, right? He's just wandering around. So time for him to get a job. So people found a job for him as a shepherd. A shepherd only has one goal they have to do. They have to pay attention to the sheep. But not Isaac Newton. No, he's still sitting here trying to come up with his little inventions and stuff while the sheep wandered away. So he was an abject failure at this whole shepherding thing. And people said, okay, well, this guy's clearly smart. I look at all his little inventions and stuff that he's doing to impress us. So they found sponsorship to send him to college. Now, his home life was kind of rough. His father died, I'm not sure if it was before he was born or when he was really young. But by the age of 2, his mother remarried. And the dude she married was such a fine fellow. He said, hey, I married you, but I did not have that as my son. And so he actually was sent to live with his grandmother. His grandmother raised him. So anyway, he gets to the higher schools, going through, and he gets to his last year, and he's still been pretty much a screw-up in school, right? Just not paying attention, not doing what teachers want. So finally gets to his last year, and he's like, crap. If I don't get my act together, they're going to make me go get a job again. And you know what? Jobs aren't fun. And so he actually got his act together for his senior year, got hired on as a house scientist, which would basically be like a lab assistant / graduate student. And so he was now doing stuff in the university, setting up lectures, giving lectures, I think. And then the greatest thing that ever happened in Isaac Newton's life happened. The Black Plague! Yay! Now, the Black Plague, of course, was very bad. It killed people. At breakfast yesterday, my son was reminding us that ring around a rosy, box full of posies, ashes, ashes, we all fall down. It's a really morbid song about dying from the Black Plague. And so they didn't want all of their bright minds at the university to give each other sickness and die. And so they sent everybody home for almost 2 years. Now, if this was me, my sister lives in Huntington Beach. You know where I'd be, right? I'd be on a flight tomorrow in Huntington Beach to spend my 18 months or so rehabilitating, not dying from the Black Plague. But Newton was like, yeehaw! I can go back to Grandma's house and do nothing but physics. Because that's pretty much how you're all feeling about this weekend, right? So he went to his grandma's house, and he worked on his physics, and he came up with the 3 laws of motion that I'm going to be introducing today. He also did some work on optics. He developed universal gravitation, and because he couldn't solve his physics problems, he invented calculus. He did all of these things in less than 2 years. And then school was back in session, and it was like, 20 years later or something that he finally published the work that he had done during those 2 years. He wrote an article and said something about coming up with a new math, and a guy from France came over and said, teach me this new math, tell me about it. So I explained to him, that guy went home, he published about calculus, and so there was arguments about who invented calculus, the person who came up with the ideas and taught the other one, or the one who first published. Obviously, by my description, you can see which way I believe, because I'm a physicist, was it Leibniz or something like that? Mathematician. Anyway, Isaac Newton, great guy. Also, great guy. Kind of eccentric. I have not read this book. Has anybody read this book? When I was teaching at PUC, somebody in the honors program got this great idea. This is one of the most influential books in natural science, so let's make the honors students read it. And then somebody who was in the sciences who had actually read it said, oh my goodness, that book is so hard to understand. We're asking people who are like not science majors to try to understand it. He wasn't very clear. Like in calculus, we used the French guy, whatever his name is. We use his symbols and stuff because they're much easier to understand. But he also wrote a lot about religion. In fact, he wrote more, I understand, about religious topics than he did about science. And he kind of vacillated between which thing he was going to spend his time on. The least great thing of all was he became a politician. Did I mention this in class already? Well, maybe one class and not the other. Yeah, that's probably right. One class, not the other. Anyway, from what I've read, he's on record as speaking only once while he was in Parliament. And so when he stood up to speak, everyone was all, "Ooh, what's the great man going to say?" He said, "Excuse me, can we close that window? It's getting a little drafty in here." So probably not a good politician, but that might be a positive character trait. So what were his laws? First, we've defined a force as anything that pushes or pulls. And the first law that Newton came up with was something to explain how forces affect motion. And I can't believe I have these in this order. I guess I'll talk about forces before I talk about his laws, because I've got everything in this place. So the forces that we deal with, we have 4 fundamental forces. Every force that we deal with in life is one of these 4 forces. Gravitational force, as far as you think about it, probably is just something that pushes us down. But as we understand it, gravity is a force of attraction between any 2 objects. How do we understand this? Isaac Newton came up with the idea that gravity is attracting any 2 objects. So the moon that orbits the Earth, the moon goes around the Earth because there is a force pulling the moon toward the Earth that we call gravity. There's also a force pulling the Earth toward the moon, the same gravity. The Earth orbits the sun because there's a gravitational force pulling the Earth toward the sun and pulling the sun toward the Earth. And so on. There's a gravitational force between me and every one of you. The gravitational force is always attractive, so I am pulling all of you up here. You feel that? Yeah, you don't, right? You don't feel it because it's very, very weak. And we'll learn about the universal gravitation. We'll learn about it. It might be the week I'm gone. Keith Reese will be teaching for a week while I am on a high school field trip. So gravity is really the most abundant force. It's the one that dominates when you talk about astronomy. But probably the force that you should think about the most is electromagnetic force. Why? Electromagnetic force is the force that holds atoms and molecules together. And so right now I am not falling through the floor. The floor is pushing up on me. Would you agree the floor is pushing up on me? By the definition of force, that means the floor is putting a force on me. But why is the floor putting a force on me? Gravity is trying to push me down. The floor is not letting me through. Why isn't it letting me through? Answer back there?
The atoms are repelling each other?
Yeah, the atoms in the floor are trying to hold themselves together. And so they won't let me push them apart. And so it's the electromagnetic force that's keeping those atoms together that keeps me from falling through the floor. It's the same force that's keeping you from falling through your chairs. And you guys have all taken probably general chemistry already. You know that atoms are almost entirely empty space, which means your body is almost entirely empty space, which means theoretically you should be able to walk through a wall because it's almost entirely empty space. You're almost entirely empty space. When I was a kid, I wasn't the brightest kid, I figured there had to be some way I could walk through a wall because of that little fact. But of course there's not, because I kind of discounted the whole atomic force. I just didn't know about it. So those are the fundamental forces. The 2 that I did not mark, the weak nuclear force and strong nuclear force, we will talk about those when we get to talking about atoms and molecules next semester. Over here on the right, I have common forces that we will talk about a lot. Each one of these is caused by one of the 4 fundamental forces. So weight, gravity, well, clearly that's gravity. So your weight, how much you weigh, is a measurement of the force of gravity acting on you. And so like I said, if I go from here to Denver, Colorado, I will weigh less because the force of gravity will be weaker on me in Denver, Colorado than it is here. Now that doesn't mean I will have lost weight, as we call it, because when we say lost weight, you really mean, oh, you've burned some fat or you've atrophied some muscle. That works too. But that's what we really mean when we talk about losing weight. Going to Denver won't make me have any less mass. it'll just make me tip the scale a little less. Normal force is the name for the force that keeps an object from going through a surface. And of course, when you say normal, unless you're a physicist or mathematician, normal means regular. But in math, normal has a different meaning. Normal is a multidimensional version of perpendicular. So perpendicular is a two-dimensional word. You have a line and you have a perpendicular to that line. Normal, since we live in a three-dimensional world, we limit ourselves to a three-dimensional definition. Now, when we get to quantum mechanics, people in physics 252, then we can talk about, an n-dimensional space or an infinite dimensional space, and normal still works there. But we will limit ourselves to normal is the idea of perpendicular to a plane. Now, I said the idea of perpendicular to a plane because perpendicular is two-dimensional. So the normal direction, if we take the tabletop, the normal direction is the direction coming out of that tabletop that's perpendicular to any line you could draw on the tabletop. So coming directly out. The normal force then is the force that's acting directly out of a surface to keep something from pushing into the surface. So as I stand on the ground, the normal force is acting directly out of the ground, which is what direction? Up. And it's keeping me from falling through. But if I come over and I push on the wall, what direction is normal to the wall? That direction. So the normal force from the wall is acting horizontally here. And if you have something that's on a slant, the normal force will be always the direction coming out of that surface. So it's a very important idea, this normal force. We're going to talk about it a lot. In this picture here, we had a block sitting on an inclined plane. So you see the F sub n, the normal force that is directed coming directly out of the surface. Force of gravity is always down. Why? Because we define down as the direction the force of gravity acts. So, of course, force of gravity is in the direction the force of gravity acts. This R here is for friction or resistance, I suppose. Tension. Tension is a force that is sent upon something like a cord or a chain or something. So tension is force through some kind of medium. And tension will apply a force anywhere it's tied on. So I have here, my string is tied to this little bob. Well, okay, stopper. And so the tension force goes parallel to the string away from whatever it's tied to, or whatever it's touching. So if I put my finger like this, what direction is the tension making a force on the top of my finger? Okay, Noah's right. Everybody look at Noah, because I can't. Okay, she took her finger down. There we go. Because I can't do it when I'm using both hands to hold this. But it's directed along the string, pointing away from my finger. What about on the bottom side of my finger? What direction is the force of tension? It's downward. Now, if you add those two together, a force like this and a force like this, if we add those two vectors, what's the method we added vectors? Tip to tail. So if I add them tip to tail, and I'll actually draw this instead of trying to do everything with my fingers, especially because if you want to look at this on like YouTube, it'll make a lot more sense. So I have the string going around my finger like this, and so it's applying two forces because the string is leaving my finger two places. So I'll call that force tension 1, and this force tension 2. Now the force of tension has a magnitude that's equal to the tension of the string. The tension is the amount of force that's being transmitted by the string. And so those are going to have the same force magnitude but different directions. So if we add those, the net force would be and so the resultant is going to go from where I started to where I ended. So the net force, what you get when you add them up, was pulling my finger down and to the right as you were viewing it, because I had those two different forces due to tension. Now, the tension can change if there's friction, and of course there is friction between my finger and the string. But you know what, in physics class, we assume things like, oh, it's an ideal pulley. That means the pulley has no friction and no mass. Yeah, because, that occurs. Springs. Springs, are things that the bigger the force, the more they stretch. And the force is proportional to how much or the amount of stretch is proportional to how much force is applied. So these are often used as scales because if you double the force, it stretches twice as far. So you just measure how much it stretched and you can read how much force is acting on to stretch it. And of course the spring, this one here, is made so I can stretch it and it pulls back. Some springs are made so if you compress them, they'll push back out. So they have a length they want to have. You can stretch or compress and they'll push back. Excellent. Okay. The last one that's going to be important to us today, friction. Friction is super, super important. Oftentimes we say, but I don't like friction. If it wasn't for friction, my car could get, really, really high fuel efficiency. That seems right until you start to think about what makes your car move. It's friction. If there's no friction, your car never goes anywhere. And things like walking. When I walk and put that foot out there, I lose my balance. I start falling forward. The next foot comes down, and it keeps me from falling and hitting my face. If there's no friction, now there are some people with this kind of muscle control. My sister, I used to teach every summer before I got married, and she'd watch, so you think you can dance and stuff. And there are people who can go from the splits to standing up using just making their legs come together. I don't have that kind of strength. If I didn't have friction, I would end up doing the splits anytime I tried to walk. And it would just be pain, and I wouldn't get anywhere. I would just try a lot. So friction is actually really vital for the way we get around in life. Right? No friction, real problems. Your car tires are designed to try to get you as much friction as possible. They have channels in there, so water and to some degree air can go up in the channels to make sure you have rubber contact in the ground even when there's, adverse conditions. And the force of friction, we'll have to talk about it later for more details. The final two here, air resistance. I mentioned in real life, there is air resistance. That air resistance depends on speed and also the shape of the object. And then there's buoyancy. Buoyancy is, there's air all around me. And the air pressure is a little bit greater down by my feet than it is up on my head. And so the result of that is the air is buoying me up a little. When I step on the scale, it actually records a weight that's slightly less than my actual weight because the air is lifting me up. Air is not very dense. If you get in water, you definitely feel the effect. Some people float. Sadly, I float because, I'm not the thinnest one in the world. And we know fat is a low density, it floats. So when I get in the water, the buoyant force is very clear because I float. And even if you sink, you get in the water and you don't drop like a rock because you have that buoyancy. It's a very small amount of net force downward. And so those are forces that we'll talk about more later. Now we can get into Newton's laws. So the first law is the law of inertia. Inertia is the propensity of an object to stay in constant motion. Now, if we go back to the days of Aristotle, and I've said this before, I think in the lab, Aristotle believed that there was a natural motion, and that natural motion was the motion I show when I'm watching a TV show. Just sitting there at rest. And so you have to do violence to an object to make it overcome that natural motion. So I have this mass set. I violently push it, otherwise known as I apply a force to it. and it moves. But when I let go, it just stops. That's what Aristotle believed. He said that's just natural for it to stop. And Newton said, nay, nay. That's like John Tennant. He said, I believe that the natural motion is just to remain in constant motion. Constant motion means constant velocity. That means the same direction and the same speed. So naturally, when I push this, it should stay going at the same speed. It does not. According to Newton, if it does not, there has to be a force that made that happen. And so this concept of the natural motion being constant motion is inertia. And so we measure an object's inertia by measuring how much matter it has. Does anybody remember what measurement is how much matter an object has? Mass. So mass is the measure of inertia. If you want to get all kinds of technical, there are two separate definitions of mass. They don't have to be the same, but every measurement has shown them to be the same. So in a class like this, we don't talk about it. One of them is a measurement of the inertia, and the other one is a measurement of its interaction with the gravitational force. They don't have to be the same by any understanding we have of physics, but it turns out they are. And so mass is simply a measurement of the inertia. So the first law says an object in motion will stay in motion, in constant motion, unless an unbalanced force acts on it. So the fact that that came to a stop meant that there was some unbalanced force that made it stop. And of course, you probably know, what was that unbalanced force? Friction, right? Friction made it stop. Now, Newton's second law makes the first law superfluous. The second law says that the acceleration of an object depends on the forces acting on its mass. Specifically, the acceleration of an object is equal to the net force acting on it divided by the mass. The reason it makes the first law superfluous is if the net force is zero, that's the condition of the first law. But if the net force is zero, what's the acceleration? Zero, which means it's going to have constant motion. So the second law actually includes the whole first law, but it has an equation. And we're going to use this equation a lot. Why? Because this equation allows us to understand why an object moved. It changed its motion because of a net force acting on it. And so we're going to do a lot of work where we look at the net forces acting on an object, gives us an acceleration, and we calculate what happens then using the kinematic equations. So while this test is going to be probably half the test is kinematic equations problems. Those aren't going away. They're just going to become the second half of a problem as we move forward. The third law is a simple statement. For every action, there's an equal and opposite reaction. Everybody's heard it. Have you heard that statement? I was going to assert everybody's heard it, and then I realized, well, maybe you have. In that statement, action means force. So for every force, there's an equal and opposite reforce. What is the reforce? It's a returning force. So that means that, and just put it in practical sense, if I push on this table, I am putting a force on the table. Newton's third law says that table is putting an exactly equal in magnitude force, but opposite in direction force on me. So I push down the table, it pushes up. And the strength of those forces are the same. Now let's take a simple practical example. I stand before you. I bend my knees a little. And then I straighten up and I can jump, right? Now according to Newton's third law, when I'm jumping, I am pushing on the ground. So what is the ground doing in response to me? It's pushing up. Now when I stand here, am I pushing on the ground? Yes, I am. If I stand here, I have the force of gravity acting downward on me. I have the force of me acting downward on the ground. And then there's always the force of the ground acting upward on me. Laura.
So if you were to jump and like go through the floor, like it wasn't strong enough.
We'll try not to have that happen.
would that be a result of the force pushing up not being strong enough? Or
It would be the object that's pushing up is not strong enough. That's right. Yes, listen.
Would that be because, like, when I was a kid, I used to do this all the time, just because I don't know. I would like to run against the wall, and then I would hit against it, and I would like push back and fall back. Would that be because of that, or?
Well, when you hit the wall, you're putting a force to the wall. It's putting a force back on you, and that force back on you is the only one that's acting on you. The force of you pushing on the wall isn't acting on you. So Newton's second law says that some of the forces are acting on an object. So we draw what we call a free body diagram, a diagram that shows the forces acting on an object. So let us take you running into a wall. Great example. Yes?
Will we be drawing free body diagrams like on exams and stuff like
Yes,
that?
you will.
Okay, so that is something.
Yeah. Yes, they're actually pretty vital. So we have, here's Leslie running toward the wall. When she hits the wall, I'm going to draw the forces that are acting on Leslie. So the forces acting on Leslie, first, we have the, pretty much always there, force of gravity acting down. And then we're going to have the force of the ground pushing up on you, the force normal from the ground. And then we're going to have the additional force here, the force normal from the wall. And so if we take Newton's second law, we say, well, what's the sum of the forces acting on Leslie? Sum of the forces acting on Leslie. Okay. And I'm going to look only in the x direction. So I'll put a subscript x and define x as horizontal. In the x direction, what's the only force they're acting on Leslie? Force normal from the wall. But according to Newton's second law, that's going to be equal to mass times the acceleration of Leslie. Because this was only in the x direction, it's only the acceleration in the x direction. And so the harder the wall is pushing back on you, the faster you're going to accelerate backwards, means your speed is going to change more. And so it was exactly, yes, that.
Yeah, which is what I'm talking about. Like, kind of like if you throw like a ball against the wall, it like bounces back. Is that what it has to do with?
Yes.
Okay.
So how do things break?
That goes back to, I think, what Leslie said, right? Wasn't it you, Leslie?
Yes.
Or, no, Lauren. About things break when you have two different strengths. Believe it or not, Wednesday in the gym, my wife and I were talking about the efficacy of a headbutt in self-defense. She's for it, I'm against it. Basic physics. If I headbutt Gila, okay, so imagine, I'm not going to even come close, but imagine she doesn't have a hat there, and I headbutt. So my forehead hits her forehead, and I hit her hard. Is it going to hurt her if I hit her hard? Yes. But what does Newton's third law say about my force on her head versus her force on my head? They're equal. So is that going to hurt my head?
Yeah.
Yes. So, like, if you were to fight, the dumbest thing would be to say, hey, let's go forehead to forehead, headbutt. Yeah! You just both hurt each other. Does that really help anyone? I mean, it might help to stop the fight. You know, both get knocked out or something. So, of course, my wife understands that. She says, oh, no. You headbutt them in the nose, which is correct. Right? If you're going to headbutt somebody, you do want your forehead to hit their nose. Why? The nose is not nearly as strong as this bone. And so the force that breaks the nose is not going to break the bone here. And so you can break their nose and cause a lot of pain, make their eyes water. And I was like, but it's still going to hurt you a lot because once you break that, you have sharp cartilage and bone there that's going to be digging in, and you know, it's not going to be pleasant. Yeah, but it's much more unpleasant for the person you hit. You know, it's a legitimate argument. I see it both ways. But the reason the nose breaks and not the forehead is because the nose is just not as strong as the forehead. You know, if you hit forehead on forehead and there are two people of equal build, you know, if you have big Neanderthal Richard and not so Neanderthal Gila, if we hit forehead to forehead hard enough for someone to break, it's going to be Gila because I've got bigger, denser bone. You know, but if they're equal, you hit hard enough and then they just both break at the same time. Yay. So I don't know how I get off on that. Yes.
Would the nose still be applying the same force as the forehead?
The nose will apply the same force on the forehead. Now, the nose on forehead will not be as strong as the forehead on forehead because the nose broke earlier and that limited the force you could reach. Okay, back to the free body diagram idea. The free body diagram is showing all of the forces acting on your object you're interested in. So in this simple case, you have two ice skaters pushing on a third. And the object we're interested in is the ice skater in blue. And so we can say, okay, what forces are acting on the ice skater in blue? As we've learned, we like to break things into directions. And so we're going to treat horizontal as separate from vertical. So in the horizontal plane, we have two forces there. In the vertical plane, we have two additional forces that they didn't show. Going back to my picture on Leslie, I showed the force of gravity down, the force normal up. I didn't do anything with them because in Leslie's case, she wasn't jumping up, she was staying on the ground. So what was her vertical acceleration? 0. Now keep in mind, if you're in free fall, as you're not touching the ground or anything else, then your acceleration is 9.8 meters per second squared down. But if you are staying the same elevation all the time, your vertical acceleration is 0. So unless Leslie falls down to the ground after hitting the wall, which is likely, then her vertical acceleration is 0, which means the force of gravity down is exactly equal to the force normal up. So that's trivial and I didn't worry about it. In my jumping example, I left the ground. I had an upward acceleration. Yay! If I had an upward acceleration, what does that tell you about the net force on my body? According to Newton's second law, acceleration is equal to net force divided by mass. So if I have an upward acceleration, what does that tell you about the net force? Well, what direction will it be? Okay, if I'm going to accelerate upward, the net force has to be upward, which means that the force upward from the floor on me is bigger than my force downward. Force downward is gravity, the force upward is the force normal. How is it possible for the force normal to be bigger? Oh, we got 2 minutes left. How is it possible for the force normal to be bigger than the force of gravity? Well, it's all in the leg muscles, right? I'm pushing, and because I'm pushing, I'm forcing my body to move. I have inertia, which is the resistance to change in motion. And so the ground has to compensate and push up harder on me than my force of gravity is downward. Now, the force my feet is putting on the ground is the same as the force the ground is putting up on me, but that's not acting on me. The force of my feet on the ground is acting on the earth. How's the earth going to respond when I jump? I'm pushing down harder on the earth than my gravity is pulling up on the earth. So what's the earth going to do? Yeah, it's going to go downward when I jump. You guys probably didn't notice that though, did you? Please say no, you didn't. And it's because the earth is so massive that the force that I was putting on the earth is really small compared to its mass. So the acceleration is immeasurably small. Okay, let's answer one clicker question and go home. Oh, actually, you know what? Don't worry about it. I'll tell you the answer and I will not save this one. We draw the free body diagrams. They're so important because we want to apply Newton's second law. Newton's second law, the sum of the forces is equal to mass times acceleration. You saw when I was talking about Leslie, that's exactly what I did. I drew the free body diagram so I could identify the forces to put into Newton's second law. That's the reason for a free body diagram.